Anubhav Ratha, if I pronounce correctly the name. Can you share the screen, please? So.
Yes. Hi, Maria. Can you hear me?
Oh, okay. Yes, so I see it very well. So I would like to introduce you. Anubhav is currently a second year PhD student at DTU, working with Professor Pierre Pinson and Professor Jalal Kazempour. In his PhD project, he's also affiliated with Vito in Belgium, and his topic is broadly on developing market frameworks for the integrated energy systems of future. So welcome, Anubhav, and you may start.
Thank you, Maria. Hello. Hi, my name is Anubhav, and I'm a PhD student at DTU in Denmark and with Vito in Belgium. And today I will discuss how we can harness the flexibility from the coordination between electricity and natural gas systems. And all of this will be to accelerate the transition towards more renewables in the power system. This is a joint work done with colleagues at DTU and at Vito. So let's get started. Gas-fired power plants actually have been a source of flexibility in the recent decades for the power system because they are fast ramping, they're easier to start and stop, but they also lie at the boundary of these two different sectors, which have been traditionally quite separate. So that's electricity system and the natural gas system. In addition to gas-fired power plants, there's also a flexibility source, which is called Linepack, and that is the ability to store gas in pipelines in a short term because gas is a compressible fluid. This flexibility source is quite huge and it's untapped relatively. To understand how Linepack works, let's look at this model of a gas pipeline. Here we saw the two nodes of the gas pipeline, node M and node U, and they have a flow QMU which goes through this pipeline. The variables pressure variables PRM and PRU denote the nodal pressures, and these are usually the quantities which are bounded by a physical limit. Now, if you look at this graph above this pipeline, the pressures at the terminal nodes are actually, they can be modulated within their bounds such that we can follow any path for the flow within these two bold, thick black lines, and we'll have the same flow, but rather we can have different amount of gas that is stored within the pipeline. And the shaded area between these two curves is actually called Linepack flexibility, and that is in a steady state form given as a function of the average pressure at the terminal nodes. If you look at absolute numbers, the amount of flexibility in Linepack available the whole of UK is about 25 times larger than the pumped hydro storage, and this is a huge amount which is available and that can be harnessed simply by coordination between the power and gas systems. And that is what is happening in recent years. So if you look at power systems across the world, renewables such as wind and solar energy have been displacing coal, and they are supported in this effort by natural gas fired power plants, which are fast acting and flexible. And while this is quite good for the environment, it also leads to more complications in the coordination between electricity and gas systems. First, gas operational constraints become more and more relevant in the day-ahead power dispatch problem, which was not the case before. And secondly, short-term uncertainty propagates from the power system side to the gas side. This often results in fuel unavailability across the gas grid, and it can also put the reliability of the gas system at risk. And as a result, it can also hamper the amount of flexibility that we can extract from the gas side to the power side. Studying this uncertain propagation is actually quite relevant because it also opens up pathways to endogenously value the flexibility that can be provided by gas system to the power sector. And this valuation then in turn be used to design new market-based coordination mechanisms or new market products. And that is the ultimate focus of our research. However, at first we would like to study this uncertainty propagation, and that is the topic of our discussion today. The research question that we study is, how do you model this uncertainty propagation and develop a unified coordination mechanism to reveal this short-term uncertainty, to reveal this short-term flexibility from the gas system to the power system? The answer to this question actually lies in doing stochastic power and gas dispatch. In our model, we consider a fully coupled power and gas system such that the central system operator dispatches both the power and the gas system agents. In a generic form, we can write this joint optimal dispatch problem like this. The objective function here minimizes the expected cost of power and gas supply, subject to the uncertainty being drawn from the worst case probability distribution. And that is shown by this min-max structure here. The decision variables extil, they contain the decisions such as the power production from the generators, the injections in the nodes of the power grid, and also gas supply injections, and as well as gas network variables such as the pressures at the gas nodes and the gas flow rates that we need to operate the line pack. We have these inequality constraints G, which we write them as the distribution robust chance constraints defined over an ambiguity set pi. And we assume that the true probability distribution of our uncertainty that the problem faces is actually drawn from this ambiguity set pi. And I will define later how we choose that. These parameters are epsilon, which are defined for each inequality constraint that denote the violation probability for each of these constraints. And in our model, physical engineering constraints such as generator limits and power line flow limits, gas supply limits are a part of these set of constraints here. And then we have the set of linear functions of X, which are defined by this H. And these include the nodal power balance and gas balance in the different nodes of the gas network, as well as they also capture the intertemporal dynamics of the line pack that we use. Finally, we have functions W, which are non-convex quadratic equality constraints. These are known as the Weymouth equations, and they govern the physics of steady state flow of gas in a pipeline as a function of difference in squares of pressures at the terminal nodes. There are two issues with the current form. The first is that the variables, as you can see, are stochastic, which means that the constraints are infinite dimensional, and that renders the problem unsolvable. Secondly, there's non-convexity in the problem due to these Weymouth equations, and they need to be convexified to ensure that we reach global optimality in our problem. Let me now discuss how we tackle each of these problems. First, to ensure solvability, we adopt moment-based ambiguity sets in our problem. We assume that wind farm forecast errors are a source of uncertainty for the problem, and we define an ambiguity set pi, which contains all probability distributions with a given mean and covariance. We assume that the mean and covariance is available from analysis of historical forecast errors in a given area. To mitigate the uncertainty in real time, we adopt recourse actions in the form of affine policies. And optimal affine policies are obtained already at the day-ahead dispatch stage, thereby reducing the cost of redispatch during the real-time operation. I'll illustrate the affine policies through a simple power network setup here. Here we have 2 wind farms and 3 flexible generators and 1 inflexible load. During the real-time operation stage, the wind farm production W tilde is actually given by the wind farm forecast given by these hats, W hats, as well as some random realization that happens, which is omega. Depending on whether there is a surplus or a deficit in the system, flexible generators here increase or decrease their production such that the overall system is balanced. The 2 equations which ensure the supply-demand balance are given here. The first one is ensuring supply-demand balance in case perfect forecasts are realized, while the second one is ensuring exact activation in any other case. As a result of this technique, the overall system is balanced in the real-time operation stage. And this technique has been quite popular in designing control systems resilient against uncertainty. In our problem, we also assume that changes in power and gas network flows can be approximated through affine functions. And this is something that we are planning to extend in our future work to drop. So adopting these recourse actions and then using this well-known analytic reformulation of chance constraints given by the Chebyshev's inequality, we convert our infinite dimensional chance constraints into convex second-order cone constraints. Now, to handle the non-convex Weymouth equations, we define auxiliary variables gamma and rho, which are sensitivities of the gas flow and the nodal pressures to uncertainty. Then we separate the terms of the equality constraint by expanding it, and we obtain 3 different equality constraints, which are terms that are independent of the uncertainty and quadratically as well as linearly dependent on them. For the first two, we relax them using the standard second-order cone relaxation, neglecting the non-convex inequality, which is shown in the top part of the figure here. Now, the same strategy cannot be used for the last equality due to the presence of bilinear terms, as you can see. So we replace each of these bilinear terms by their McCormick envelopes, and we convexify this constraint as well. So adopting these two steps allows us to convert the non-convex Weymouth equations into second-order cone and linear constraints, making the overall problem convex and solvable. In the end, we obtain the final tractable form of our original stochastic problem. It is a second-order cone program that is solvable quite efficiently by off-the-shelf commercial solvers. And in a nutshell, the way the model works is that we have mean and covariance of the forecast errors, which are extracted by the central system operator from the historical data. And they're used by the operator to not only assign an optimal dispatch schedule to different agents, but also optimal flexibility procurement is reached with in the form of affine policies. The parameters here, epsilon, are chosen such that they indicate the risk preference of the market, of the system operator. And naturally, 1 minus epsilon is the confidence then the chance constraints hold. To test our methodology, we selected the IEEE 24-bus reliability test system, which is coupled with a fictitious 12-node gas system. 7 out of the 12 generators in our system are gas-fired, and we have 2 wind farms, and there are 3 gas suppliers in the coupled gas network. We obtained the bounds for defining the McCormick envelopes by solving a deterministic version of our problem. And in that deterministic version, we assume that perfect forecast of wind farm production is realized. We assume that all the violation probabilities for the chance constraints are identical. And we finally use 1,000 wind forecast scenarios collected in Denmark to obtain and estimate the mean and covariance, which is used by the system operator. The figures here show the coupled power and gas networks, and gas-fired power plants that couple these two systems together are shown in these red rectangles.
Anubhav, you have 1 minute.
Coming to results now, the figure here shows the optimal dispatch schedule and the affine policies for the power generators, which are grouped into gas-fired and non-gas-fired power plants. We observe that in the hours when specific generators are not dispatched, or if they're fully dispatched, then they are not assigned any affine policies. Similarly, lower cost of flexibility is preferred also for the gas suppliers. On the gas side, we also observe that the gas injections are made highly in the hours in the beginning, such that the gas-fired power plants can actually extract gas from the system in the later hours. To test the exactness of the convex relaxations, we also used a metric which we call normalized relaxation gap. And this metric allows us to evaluate the exactness of our relaxations. And we observed that the exactness obtained for the second-order cone relaxations for the terms which are quadratically and independent of uncertainty are actually satisfactory for this case on the left. And the remaining inexactness can be actually attributed to the nature of the gas network, which is non-radial in our case. For the McCormick relaxation, we obtained that because we obtained the bounds quite trivially, we observed that the relaxation is quite loose. And in fact, for some hours, we have adverse negative values of these bilinear terms that are obtained. And as a result, the normalized gap is actually exceeding 1. Lastly, we also did some ex-ante simulations to evaluate the value of the quality of our solution. And we observed that with increasing confidence level that is desired by the system operator, actually the cost of the dispatch increases as expected. And with that, we receive a higher confidence level on the chance constraint being held. We also checked the susceptibility of the various constraints into violation. And we observed that generator production limits and gas flow unidirectionality constraints and the gas supply bounds are the ones which are most susceptible to violations. The results, specifically this part, we observe are quite network specific though. Finally, to conclude, in this work, we performed a tractable reformulation of stochastic joint power and gas dispatch based on affine policies. And we showed that cost-efficient dispatch and flexibility procurement from a variety of sources can be done, keeping the spatio-temporal uncertainty in mind. As next step, as I mentioned, we would like to consider generalized decision rules for our gas network uncertainty. And we'd also like to tighten the convex relaxations using iterative algorithms or using other techniques. It would be nice to extend this coordination in a market context, which is quite natural next step for this work. And we would like to perform out-of-sample simulations just to evaluate and provide guarantees of optimality and feasibility. And finally, limited information sharing also makes this problem more relevant to the real world market case. Thank you for your attention, and I would be happy to answer your questions now.
Okay, thank you very much for the nice talk. Do we have any questions from the audience?
Maria, I have a question, but I'm not able to type into the Q&A.
Okay, you're welcome to do so here.
All right. Okay. So so then I will ask you directly, Anubhav. This is Lina here. So yeah, first of all, very nice presentation, nice paper. So I was just wondering, you were mentioning that you were doing this verification through the simulation.
Mm-hmm.
And so I was wondering, so you have this assumption in your paper that sort of the flows and the pressures will vary linearly with the power uncertainty. So I was wondering if you had done any simulations to check if this assumption actually holds. And then also I was actually curious if you tested against like a dynamic gas flow, or if you, I mean, if you had like a dynamic gas flow simulator.
So actually, what we observed is that, first of all, the main focus of our work was to model the uncertainty propagation. So at the first stage, we did not consider about doing out-of-sample simulations or to actually test the relationship of real-time flows with the uncertainty. And we realized, midway that actually it's not really affine. It's not an affine dependence on uncertainty, and that's not surprising because of the nonlinear dynamics. But we thought that this way approach shows the modeling framework, and then later on we extend it with generalized decision rules, which could be, for example, conic decision rules or nonlinear decision rules in general could help us to make it more relevant to the real world.
Cool, thank you. Makes sense.
Thank you, Anubhav. There is one related question from Patrick Panchatici. What is the time step in the work? Could you address ramping issues and propagation delay in gas pipes? Partially you answer this question, but you can give some more insight.
Yeah, sure. So the time step that we used is hourly. And in this case, yes, so the modeling is general enough to include any ramping constraints, because we consider this large covariance matrix, which captures both the temporal as well as spatial errors in different parts of the matrix. So yes, we can consider ramping constraint. Regarding the propagation delay in gas pipes, we believe that the Linepack dynamics, which we model, takes that into account already. And however, we still need to make some more, as I was mentioned to Lina, more real-time simulations to actually understand that in more detail. I hope that answered the question.
Oh, yeah. So we have one more from an anonymous attendee. How is it possible to consider general decision rules? Is it possible to introduce learning-based decision rules to capture the effect of uncertain parameters on decision rules more accurately?
So what we do with this affine policies or affine linear decision rules is actually we project the nonlinear reality into a linear space, and that's an approximation. And if we do general decision rules, we'll essentially be lifting our problem to a sort of a nonlinear domain. It's already in the form of quadratic constraints. So quadratic decision rules, for example, could be a natural fit. And given that the theory for that is existing, but not much has been implemented for the gas networks, that is something that we are considering. But no, learning-based decision rules is something that we have not discussed actually to make it work. But that would be an interesting future work as well.
Okay, great, Anubhav. Thank you very much for your nice talk.